complex exponentials, we also need to give a meaning to the expression e to the power z when z equals x plus I, y is a complex number. The theory of infinite series, as developed in Chapter 11, can be extended to the case where the terms are complex numbers, using the Taylor series for e to the power x times, excuse me, that is not times, open 11.10.11. As our guide, we define equation 4, e to the power z equals the sum from n equals 0 to infinity of z to the power n over n factorial equals 1 plus z squared over 2 factorial plus 3 cubed over 3 factorial plus ellipsis. And it turns out that this complex exponential function has the same properties as the real exponential function. In particular, it is true that equation 5, e to the power z sub 1 plus z sub 2 equals e to the power z sub 1 times e to the power z sub 2. If we put z equals y where y is a real number in equation 4 and use the facts that I squared equals negative 1 and I cubed equals I squared I equals negative I, and I to the fourth power equals 1, and I to the fifth power equals I, we get e to the power I y equals 1 plus I y plus open I y close to the power 2 over 2 factorial plus open I y close cubed over 3 factorial plus open I y close to the fourth power over 4 factorial plus open I y closed to the fifth power over 5 factorial plus ellipsis equals 1 plus I y minus I squared over 2 factorial minus I y cubed over 3 factorial plus y to the fourth power over 4 factorial plus I times y to the fifth power over 5 factorial plus ellipsis equals open 1 minus y squared over 2 factorial plus 4 plus y to the fourth power over 4 factorial minus y to the sixth power over 6 factorial plus ellipsis close plus I open y minus y cubed over 3 plus y to the fifth power over, excuse me, that was y cubed over 3 factorial plus 5y over 5 factorial minus ellipsis close equals cosine y plus I sine y. Here we have used the Taylor series for cosine y and sine y, equations 11.10 and 16 and 11.10.15. The result is a famous formula called Euler's formula. Equation 6, e to the power I y equals cosine y plus I sine y. Combining Euler's formula with equation 5, we get equation 7, e to the power x plus I y equals e to the power x times e to the power I y equals e to the power x open cosine y plus I sine y close. Example 8. Evaluate e to the power I pi and part B e to the power -1 plus I pi over 2. Sidebar, we could write the result of example 8a as e to the power I pi plus 1 equals 0. This equation relates the 5 most famous numbers in all of mathematics: 0, 1, e, I, and pi. Back to the text solution. A. From Euler's equation 6, we have e to the power I pi equals cosine pi plus I sine pi equals -1 plus I of 0 equals -1. Part B, using equation 7, we get e to the power -I plus I pi over 2 equals e to the power -1. Open cosine pi over 2 plus I sine pi over 2 close equals 1 over e times open bracket 0 plus 1 open 1 close bracket equals I over e. Finally, we note that Euler's equation provides us with an easier method of proving de Moivre's theorem. Open bracket r, open cosine theta plus I sine theta close bracket to the power n equals open r e to the power I theta close to the power n equals r to the power n times e to the power I n theta equals r to the power n times open cosine n theta plus I sine n theta close.